Good morning. Last several classes we have been talking about heat treatment of steel, and today we will try to finish the points which has not been discussed so far. If you look back, you will find that under this lecture we have covered this. We talked about these isothermal transformations. We talked about isothermal transformation kinetics. We talked about austenization process. We talked about CCT diagram, how they are made. We talked about some common heat treatment processes, and part is which is left out. I think last class we introduced, we discussed hardenability. Today we will see a little more some important aspects of hardenability, and we will also try to look at how alloy additions mean other than carbon, how does it affect the transformation diagram, both TTT, CCT and phase diagram. And if you try and recollect the previous thing, we introduced a this Gemini hard. So, we introduced the concept of hardenability, and and it was told that hardenability gives you a measure of the depth of hardness that you are likely to get if you austenize a piece of steel and then quench in certain medium or cool at a certain rate, to what depth you will get that desired hardness that you are looking for. And we define certain factors like quenching severity. How do you define cooling rate? So, we talked about a factor called H factor, Grossman severity of quench factor, and we also talked about ideal critical diameter, which is a material property in a way. So, this gives you the depth of hardness that you can get in a steel if it is quenched from the appropriate austenizing temperature in an ideal medium where you have infinite severity of quench. Then di is the depth up to which you will get complete hardening, and complete hardening does not mean that hardness is uniform from surface to the center of this job, but it means that you have hardness at the surface, which is the maximum hardness. At the center you have a hardness which corresponds to 50% martensite and 50% transformation product, and for 0.8% carbon steel, hardness of this 50% martensite, 50% perlite is around 54 RC or around 55 RC. And since to determine ideal critical diameter by following Grossman method, you need a very large number of samples, and the test procedure is also quite involved and time taking. And a quicker method is a Jomini end quench test, where one uses a gradient quenching. And here you will find this is a pictorial representation. Red means it is hot and you are trying to cool the bottom by spraying water, and you spray water from a certain fixed distance and it touches the surface and falls out in the form of an umbrella or a curtain kind of thing. And so, this is where you have the maximum cooling rate, and the cooling rate decreases as you move along the length, and here you have the less minimum, this end will be the minimum cooling rate. And after the end quenching is done, after the sample has cooled down to room temperature, you take out this piece from the fixture, and this specimen also, these dimensions, approximate dimensions are given, and these tests are actually empirical tests. So, it is better to follow the standard dimensions which are given here, and then what you do, you grind make this point smooth, say since it is round, it is a cylindrical sample, and you grind off the top surface, and along this surface you keep measuring hardness at different distance from the quench end, and after that you make a plot this hardness against the distance from this bottom end, and if you plot you get a hardness profile something like this, and then say this is the maximum hardness that you will get near the surface where you have the maximum cooling rate, and somewhere down below you find out where it is the hardness corresponds to 50% martensite, 50% perlite, say 54, and then you say that this is my depth of hardness. And in fact, this test, this is a single specimen test, and this became so popular, people have worked out and found out correlation of this Jomini hardness depth. This is the Jomini hardness depth x, and this can be converted into ideal critical diameter. And in fact, these are such types of plots are available, and which helps you to convert the Jomini hardenability depth, hardness depth to ideal critical diameter. So therefore, this is the most popular method for determining hardenability of a particular steel. Now, we introduce a concept of ideal quenching. Let us look at it little critically. You have a sample here where what is shown, I have tried to quench, and surrounding, it is surrounded by water, it is quenched in water. So, it does not, temperature does not immediately come to room temperature. Definitely the surface will be at the lowest temperature, center will have the highest temperature, and with time this temperature difference will go on decreasing, and the rate at which will decrease will determine our ability to extract heat from the surface, which will be determined by convection. That means, within the water how fast we are able to take out the heat, and within the job this rate will be determined by the conductivity of the material, a rate at which heat can flow from center to the surface. And obviously, this convection heat transfer. So, there will be. So, we define a severity quench factor, which was defined by Grossman. It is a very average heat transfer quenching severity, which is taken as a ratio of H, which is the convective heat transfer coefficient, and over twice the thermal conductivity of the material. So, we say that ideal quenching medium is one where H is infinity. What does it mean? The small h is infinite. So, that means as you quench, what we can say that immediately this surface comes to that heat transfer, this is infinite. What we can say, the surface immediately comes to the temperature of that surrounding, say if it is the quenching medium. So, that is the maximum that we can think of, but we will little while we will see that it is far from reality, but nevertheless many cases one does define such cases where you have very extremely high or infinite, it is an hypothetical quenching medium where H is infinite. And I will leave it to you to examine the dimension of these heat the H, and you will find this dimension comes out to be 1 over length. So, most of these heat treatments still people report, many of these charts you will find people use inch as the measure of distance, but which you can take that 1 inch is equal to roughly 25 millimeter. So, these such approximations are always used in engineering. Now, if you try to find out, so this will be 1 over inch or 1 over a meter or 1 over centimeter, that will be the dimension of this severity of quench. And here we have listed some of the common severity of quench. Say brine with severe agitation, you can get 5, H is 5, and H is 1 for a normal water quench without agitation. whereas if you oil quench, in that case it can be depending on whether you have agitation or no agitation, you will have certain value for this quenching severity, like 0.5 for oil quench with agitation. And here, so you have a chart which gives you the relationship between the critical diameter and ideal critical diameter, and this is the plot for infinite quenching severity, that is H is equal to infinity, and you will find that the slope of this line is 1. So, that means if DC critical diameter is 1, DI is also 1, whereas in other cases if you find that for a particular material the DI you find that it is say 2 inch or something, which is somewhere here, and then if you quench in oil, then you can find out this is the depth up to which you can get practically speaking, that means up to the depth you get a hardness corresponding to 50% martensite and 50% barlite, which is definitely much lower than the ideal diameter. Now, a quick look at the heat transfer, process of heat transfer when you quench, and let us see look at it a little more critically. Say here if you quench, this is a section of a job which has been quenched in water. When you quench, it has a very high content of heat. So, suddenly what happens, a blanket, a steam blanket will form over here, and when a blanket, steam blanket, you know, this has a relatively low conductivity and it is stagnant. So, you have a poor heat transfer coefficient. So, therefore, here you find as long as this steam blanket stays, you have the rate of cooling is slow. So, this is the region, and the rate of cooling starts increasing once bubbles nucleate, and this bubble nucleation, it sets in a severe or violent agitation in the surrounding area. And once this is called the nucleate boiling. Once this nucleate boiling starts, you have bubble formations which results in severe this agitation, and therefore, the cooling rate increases substantially. So, you have maximum cooling rate in this region, and later on when this boiling stops, then the normal convection takes over. So, this is the case of a normal convection, and it may take very long time. And if you plot that cooling curve, it may have something behavior may show like this. There are 3 distinct regions where you have steam blanket which prevents heat transfer, so slow rate of cooling, then nucleate boiling, and this is what one should try to get as quickly as possible to get an ideal quench, and then finally convection. Now, the point that comes up here is that the purpose of cooling is, so you have to organize it. The heat extraction rate must balance the rate at which you are able to extract heat from the surface must by this convection, or if this is from outside convection or nucleate boiling or whatever is the mechanism, the rate at which you are able to extract heat must balance the rate or that heat at which heat that flows from center of the job to the surface. And therefore, it is possible to apply this concept of heat transfer to derive some very simple relationship. Now, which is listed here, this gives the rate at which the heat transfer, this is the amount of heat flux which comes out from the surface. So, which will be proportional to the temperature difference. Tf you can say is the final temperature of the job, or you can say this is the temperature of the quenching medium. So, let us say this is room temperature, and this is S is the surface temperature at any time, at any instant. So, if we say that it is the initial, just when you quench, you can say that this temperature is the austenitization temperature right at T equal to 0. This is the temperature, whereas at any instant or you can say this is the temperature which is a function of time, and H is the effective heat transfer coefficient. And what you can see here, heat transfer coefficient, it changes with the time depending on the actual mechanism, but Grossman approach, it assumes a constant or an effective heat transfer coefficient, and let us assume that it has an average or effective heat transfer coefficient. So, this is the part that rate at which the heat you can extract from the job by convection from the surface. But the maximum amount of heat that you can extract through convection is also balanced by the amount of heat that comes from the center of the job, and this is by conduction, and which is given by the temperature gradient, temperature at the surface minus temperature at the center. So, this gradient and this should balance, and this is proportional to thermal conductivity. So, therefore, temperature at the surface, the temperature gradient at the surface, therefore, this x is the distance within the job. So, temperature gradient at the surface you can say is a function. This is how you can represent x is the distance from the surface, and this is can be written like this. Now, heat transfer within the steel, of course, within the job it can be solved by normal heat transfer, conductive heat transfer technique, which is quite well established, and it can easily be done by Fourier series kind of solutions. But let us look at a much simpler approach which will be quite useful in designing a heat treatment process. Now, here often one uses in heat transfer one uses some normalized temperature, normalized distance, and what you can think about a normalized temperature U, which is a difference of two temperatures. This is the temperature at any instant or temperature at the surface at any instant T minus the final temperature divided by T I, which is the initial temperature, that means austenitization temperature, this is initial, minus T final. Final temperature means the temperature of the surrounding or temperature of the quenching medium. And reduced distance, one can say that x you can say as a ratio, z is the reduced distance, is x of radius of the job or half the thickness of the job. And if you do that simplification, this expression will transform to this, and finally, you write with du dz, this reduced distance, you get this term. Now, look at this, what you are getting here. See, h over twice k, we have assumed this to be we have assumed that severity of quench H as defined as H over twice k. Now, look at this here, if you go back here, if you divide this by 2, this becomes twice r here. So, H by twice k is capital H severity quench and times diameter, 2r is the diameter. So, this entire expression reduces to quenching severity, diameter of the cylinder times u. So, now look, what is the dimension of HD? HD, H is a dimension, H we have said that it is 1 over distance, or to say let us say 1 over centimeter, and diameter is centimeter. So, HD it is a dimensionless constant, and it is quite a useful parameter in designing heat treatment, and you will find that all cases, all components where if you find that HD is has the magnitude is same, then what you can say their relative that cooling characteristic will be similar. So, therefore, all cylindrical Campbell say of diameter, if it is quench in medium such that the H d is constant, they will have relatively similar cooling characteristic. And what does this mean? So, this means say if you have let me take a sheet here. Say suppose if you have a job here which has a particular diameter, this is the diameter, and it has you have quenched that is in a medium, so that this product H times d is low. So, in that case this H d in any case, whether if the diameter is this or diameter is small, but H d is same. So, here also say suppose H d is equal to, here it is 2, here also H d equal to 2. So, depending on if it is low or high, it will determine the nature of the temperature profile that you have. So, if H d value is low, you will find that this profile will be shallow, low profile. So, low H d. So, here also if you maintain the same low H d here, here also you will get a similar low profile. So, characteristic, that is relative cooling will be same. So, using this concept, but if it is if H d is high, you will find the other end, if H d is high, say suppose you have say this is 5. In that case you will find there is a large, it will be symmetric. So, this temperature gradient, so this temperature here you have a shallow temperature gradient, in this case you have a sharp temperature gradient, and it is possible. So, this is a very simple concept which helps you to design that quenching process and then that quenching technique, so that you get the desired hardness with minimum distortion. And let us now look at the factors that affect hardenability. Part of it was explained last class, and there are primarily 3 main factors which determine hardenability. One is austenite grain size, and we talked about a method of determining austenite grain size. ASTM method is like this: n is the number of grains that you see at 100 magnification at 100x, and n represents number of grains in 1 square inch. And this is n is an index which is a number. So, that means if n is, let us say if n is 6, the number of grains you will see in 1 inch square, that will be 32 grains you will find. So, higher the number means finer the grain, and we have seen that if you have high number or a high austenite grain size or a high that austenite grain size number, so that means it is a fine grain structure. If you have a fine grain structure, then you have a large number of nucleation site for diffusion control transformation to take place. So, therefore, finer grain will exhibit lower hardenability, which is shown over here, and last class I tried to explain with the diagram about the effect of grain size on hardenability. So, this is a plot which shows that ideal critical diameter as function of carbon content for a. So, that means for a given grain size, austenite grain size, say austenite grain size number 0.8, what it shows, as you increase percentage carbon, ideal critical diameter goes up. And for the fixed carbon, say let us say 0.5, this is over here. for this fixed carbon. As you increase as you make the grains coarser, or if you control your austenization time, you keep it for longer time or you keep it at a higher austenizing temperature to grow higher grain, you will find as the grains become coarser, the hardenability improves. But this is not a very favorable way or technique of improving the hardenability, because coarse grain structures have poor mechanical property, and we have talked about it earlier. So, you get a poorer toughness, and toughness is an important criteria for material selection. Therefore, generally even in hardenable steel one would like to have fine austenite grain size. So, this is not a favorable way of improving hardenability. So, therefore, we do not consider this. So, only the two factors which can improve hardenability is by increasing carbon content, and another is increasing alloy addition. Now, if you look at the effect of alloy addition on hardenability, people have, these are all empirically and derived results. I have taken this from handbook, and here this column gives percentage wet percent carbon, and I have given this approximate value for different the austenite grain size number. This carbon with steel, this is the hardenability for carbon, plain carbon steel containing a particular amount of carbon, but having austenite grain size number 6, and this is the austenite grain size number 8. So, for a given carbon content you find that, look at, you have a coarser grain, say look at over here, the coarser grain has higher hardenability. So, this is a factor, hardenability factor. So, this has a, you can say this has a higher hardenability, say 0.22 is the factor, whereas here it is 0.18. So, that means up to 0.22 inch you get a proper hardness, whereas in this particular case up to 0.18 inch if your grain size is fine. Now, any alloy element you add, they help or they improve the hardenability. Most of the alloy elements additions, and in fact, one of the primary reason for adding alloy element to steel is to improve its hardenability. As you see, suppose manganese, you go on increasing manganese. So, these are the hardenability factor. See at 0.5%, and this is a synergic effect, you know, at 0.5% carbon steel, the factor is 1.17, but its effectiveness increases if amount of carbon increases. With 0.35, that is a synergy, that same amount of see this is about 0.5, whereas here when you have a 0.35% manganese, then this is this. So, always, and it need not necessarily be linear, but these are the values. So, this is if you add 0.05% carbon, this is your hardenability for effect, increase ability of manganese to increase hardenability of the steel by this factor 1.15. If it is 0.1, then this factor is 1.33. Likewise, this is for silicon. So, compared to silicon, the ability to increase hardenability by manganese is higher. You can see here, see for 0.35% of either manganese or silicon, you know, here you get a higher hardenability factor. So, this is the factor for nickel, this is the factor for chromium, and this is the factor for molybdenum. So, most similarly you will have factors for each all the common alloy elements, and these are available in the form of table. And if you want to find out the hardenability in terms of ideal critical diameter, you have to look information that you have to provide is austenite grain size, carbon content, and other alloy additions which are there. And then you can look up table, say like if one, say you look up if his austenite grain size number is 8, and carbon content is 0.1, then this first factor is F1 is 0.1, then you check up how much manganese it has. If it has 0.3 manganese, then you have to multiply F2 is 2, multiply this by 2. Similarly, you find out factors for each of these and you get a value magnitude for Di. Now, effect of alloy addition of hardenability, as mentioned, that with the exception of cobalt, all alloy element improves hardenability. And now, but hardness depends primarily by carbon content which is shown in this plot over here. Say suppose this is a carbon steel which has relatively low hardenability. If you look at the Jomini hardness plot with that this is the surface hardness. So, this is, let us say this is around 0.6% carbon steel, and with no other alloy element, primarily carbon, it will be a shallow hardening steel, and this is the plot, the Jomini hardness profile. Whereas, if you have a steel with alloy content, possibly here carbon content is low. So, carbon content is over here, and then but its depth of hardness is much more with alloy content. So, that means alloy addition, and in fact, one of the main advantages alloy addition helps reduce quench severity that is required to get same hardness at a particular depth. Now, let us see why does all alloy element addition, how does this affect the heat treatment procedure. Now, two things we can think of an alloy addition will do. One, it will alter the phase diagram, and second, it can alter the transformation diagram. So, phase diagram means, say this part, if you recollect, this is the steel, say normal carbon steel. So, this is gamma, this is alpha plus cementite. But if you add alloy element, what will happen? These temperatures, it is no longer a binary system, it becomes a ternary or quaternary system, and therefore, the phase diagram, the nature will change. And let us not go into the total complications of ternary or quaternary diagram, but what we can visualize these critical temperatures for a particular, say this is say 0.4% carbon steel. If alloy addition is added, what will happen to its microstructure? How do you interpret? Then we have to see that alloy addition, what does this do? It can do two things. It can change this critical temperature, it can change this temperature A1, it can change this these temperatures A3 temperature. It can also change the composition of the eutectoid. So, let us first look at it which is shown over here. See, effect of alloy elements, depending on alloy elements, say carbon, if you have carbon, the eutectoid temperature is irrespective of percentage alloy. The carbon content, you have the eutectoid temperature around 723, let us say. But if you add alloy elements, say like nickel or manganese, then you will find it brings down the critical temperature. So, these are called austenite stabilizer. So, these are the elements which try to bring down the temperature in which the austenite temperature range in which austenite is stable. Here carbon also included as an austenite stabilizer, primarily because if you look at this phase diagram, you can see you increase carbon content, that austenite is a temperature, it goes on decreasing. But yes, this part, but these are not important, very few steels, except for tool steels, we rarely use this part of these are rarely used application wise. Bulk of this application will be in this regime, and therefore, for most cases what we can say that carbon is an austenite stabilizer within this limited range. So, nitrogen also has a similar effect, and all these alloy elements which are listed here, they make austenite stabilizer. In fact, there are certain grades where austenite can be made stable even at room temperature with relatively high amount of nickel or manganese. One very common austenitic stainless steel, many of you are familiar, you find that this is primarily because this has high amount of nickel and it is austenitic, and austenite is a non-magnetic. So, whenever normally you go and buy stainless steel, you check with that with a magnet. So, that says that either it has a high amount of nickel or manganese, that makes the austenite, which is normally stable in plain carbon steel at very high temperature, they become stable even at room temperature. So, as against this you can think about there are certain alloy elements, and many of these will find they will have a body centered cubic structure, chromium, tungsten, moly. So, these are the elements where they are called ferrite stabilizer. They increases the temperature, they raise these critical temperatures, like whatever is shown here. This eutectoid temperature goes up with addition of titanium, molybdenum, tungsten, silicon, chromium, and their relative power may be different. So, primarily what is happening? So, you have a broadly two classes of alloy element. One is ferrite stabilizer, which increases the critical temperature, another group called austenite stabilizer, which brings down the critical temperature. Similarly, these alloy addition also alter the carbon content of that eutectoid structure, which is shown here, percentage carbon in eutectoid steel. Here, if you add, it goes down irrespective of whether it is an austenite stabilizer or a ferrite stabilizer. As you increase these alloy element, eutectoid composition shifts. So, that means if we look at this over here, so this point shifts to low carbon content. If you look at this sheet here, this eutectoid point, if it shifts like this, and so that means if you have this 0.5 carbon, you approximately say that here pro-eutectoid ferrite amount is around 50%, but if it moves here, what will happen is amount of pro-eutectoid ferrite will decrease, because pro-eutectoid ferrite is proportional to this part. So, if this shifts here, amount of pro-eutectoid ferrite will be proportional to this over the total. So, therefore, this will suppress presence of, that means eutectoid percentage perlite will increase with as you increase alloy element. So, this is one important point you must remember, and then effect of alloy elements also determine affects this transformation kinetics, like both it affects both time temperature transformation diagram as well as CCT diagram, and in fact, this effect is shown over here. All alloy elements except cobalt slow down diffusion control transformation. All alloy elements, they slow down this diffusion control transformation, and if let us look at this diagram, see this TTT diagram is shifting to the right side. The MS temperature, MF temperature, they go down. So, that means there is chance of having more amount of that retained austenite is increases with in alloy steels. Similarly, it is also possible that this alloy addition will affect both perlite and benitic, perlitic and benitic, this kind of eutectoid transformation, high temperature eutectoid and low temperature eutectoid transformation Pearlite is a high temperature eutectoid transformation, bainite is a low temperature eutectoid transformation, and these are affected differently. Particularly, let us say for with chromium, this slows down pearlitic transformation, but not bainitic. So, in this particular case you get a separate type, you get another BS kind of a temperature below which you get a, like here is a pearlite starts forming below this temperature. Similarly, you can think of a bainite start temperature, below this temperature you expect bainite to form isothermally. And also we mentioned that under continuous cooling you do not get chance of getting bainite in plain carbon steel is remote, but in alloy steel even by continuous cooling you can get bainitic structure. Now, this alloy addition also affects tempering process. We looked at the tempering process. Tempering is a diffusion control phenomena. Tempering is a diffusion control phenomena, and if you look at if you recollect the structures that we talked about, and let us look at the screen, that most alloy element will slow down the tempering kinetics, and some alloys like tungsten and moly also give secondary hardening. So, what happens, this is a normal hardness versus a hardness as it drops with increasing tempering temperature. This is the tempering temperature, this is the Rockwell hardness, this is Asquith hardness, and with increasing time temperature keeps dropping. You have three distinct stages of tempering. This is the first stage of tempering where you have high carbon martensite gets converted into low carbon martensite with low C by A ratio plus possibly epsilon carbide. Second stage where predominantly that retained austenite breaks down, and also this low carbon martensite also get converted into finally into ferrite plus carbide, and this epsilon carbide is also replaced by cementite, and towards the end the cementite starts growing. So, that is why this hardness keeps dropping. If you increase the alloy content, the rate at which these processes take place, that slows down. They control diffusivity because all this transformation is diffusion control. So, therefore, they become slow. Whereas, if you have moly and when these kinds of alloy elements which form some give secondary hardening, they form certain carbides which are coherent with the matrix, and this is some kind of precipitation hardening takes place here in this stage, that is why hardness goes up again. So, this is called a secondary hardening, and these alloy elements they have different ability to be distributed either in the matrix or in the carbide. Particularly these elements which are listed here, niobium, titanium, vanadium, tungsten, moly and chromium, they are most likely they are they will be present in carbide, whereas nickel will be likely to present in austenite or later on in ferrite. Now, during tempering often we come across loss of toughness, and there are two kinds of which is called embrittlement. So, and this is also connected very well with alloy addition as well, and there are two kinds of temper. One is called temper martensitic embrittlement, and this is takes place in these temperature ranges either at 250 or 350, and these processes are also diffusion control. They are some kind of precipitation, and these are also diffusion control process, and sometimes the kinetics is such that this is fastest at around 250, and with some alloy additions or others it can change to 350, and this type of embrittlement is also known as one step temper embrittlement. This occurs once only during tempering. There is another kind of temper embrittlement. This is a relatively you get if a material is steel is tempered at relatively high temperature around say maybe 600 degrees centigrade, and after that if you slow cool you find there is a loss of toughness. this is called 2 stage, and it reappears. Say suppose if you quench, but again you heat it to the temperature range around say 500 degree centigrade, it reappears if it is tempered and the same temperature range. And how do you detect this loss of toughness? So, this is actually this loss of toughness is the best way to measure is Charpy impact value, Charpy or I-Jod impact value, where you try to a notch specimen is fractured under a hammer as a pendulum kind of an hammer, and you try, and we talked about it in earlier classes, and try to find out how much energy is absorbed by this notched specimen to fracture. And you will find that once it becomes embrittled, it has a very poor toughness, impact value is low. Martensite as such has low toughness, but as you start tempering, its impact value starts increasing, and suddenly you come to these temperature ranges, again it starts decreasing. It also has higher ductile to brittle transition temperature, and characteristic, if you look at the fracture, it will exhibit intergranular fracture. Now, effect of tempering on toughness, say particularly let us consider temper martensitic embrittlement. I said this is around this temperature range, it takes place around 250. And here the hardness, this is how the hardness is dropping. From the hardness you can't make out whether the material hardness is low hardness, does not necessarily mean high toughness. Look at here, the hardness has significantly dropped down, but again the toughness was beginning to increase with the tempering, but there is a drop over here. Thereafter it goes on increasing, and this type of embrittlement is primarily associated with segregation, like phosphorus segregation, some of these, and they segregate to prior austenite grain boundary, and some of the other segregating elements, these are not added intentionally, they come by chance, and their amount is extremely small in the total alloy, but when they segregate, the grain boundary concentration becomes extremely high, and people have determined these by OJ electron microscopy, the amount, and it becomes substantial. They do not show up as precipitate, but the concentration is quite high at the grain boundary. So, therefore, if you have so the problem comes up, if you have a fine grain, then you can say the segregation chance will be less that amount, whereas if you have a coarse austenite grain, that is also another reason that effect of this kind of embrittlement will be even more severe. To overcome this, you have a fine grain or fine prior austenite grain size, and secondly try to control these tramp elements which are not supposed to be there. And there are also people have thought about, one is a segregation, another people think there are actually some amount of high carbon retained austenite. If you see the austenite which forms towards the end, sometime they can have high carbon content, and at lath boundaries these retained austenite, they have high carbon content, and this boundary converts into ferrite plus thin carbide plates, and this makes it brittle. Now, temper embrittlement, which is actually a 2-stage process. So, it takes place as many times heat it to the susceptible temperature range, and this is shown here. This is the normal hardening, you heat it to austenite, quench, and then you temper it at 600 degree centigrade, and if you try to cool it, if you quench it after tempering, then you find the toughness is high, but if you cool it slowly, then you find the toughness is low, and this is the plot which shows the Charpy V notch value against tempering temperature. So, this is that 250 tempering, this does not occur second time you temper, you do not get this, but this is can be this is reversible, this can occur again. So, and next is it is goes on, and if you quench after this, it follows this path, and in fact this quenched I mean after like 4340 steel, which is a very popular steel, and this is used as a spring and many other very critical application, ultra high strength steel. This gives best combination of strength and toughness if it is after hardening and subsequent tempering, if it is oil quenched, you get this. But if you air cool, then such steels are prone to this kind of embrittlement. This embrittlement also is primarily because of segregation of these elements and also their interaction with these alloy elements. And this does depend on these alloy elements, and there is one element which actually helps remove such kind of embrittlement. And this steel can be de-embrittle. Say if a steel has become embrittled, then you can give a second treatment, and then after that you oil quench, it is no longer temper embrittle. But you heat it again to this temperature range 500, 550 degree centigrade, hold it, then you will find it has become embrittle. And in fact, that many of these power plant steels which are used in many cases hardened and tempered condition, and they are kept for very long durations at around 550 degree centigrade. So, they become they are quite prone to such kind of embrittle, that service type embrittle. And here after this, if you remove a material, if you give this kind of a heat treatment again, you can restore the toughness. And temper embrittlement is also associated with increases ductile to brittle transition temperature. This is say suppose the steel which is susceptible to temper embrittlement, if you fast cool, if you quench after tempering and you determine that Charpy V notch value at different test temperature, you get a plot like this, and here this is the place where you can say you can get a 50% brittle, 50% ductile fracture. So, what you can say, this is the transition temperature. Below this you say the material is brittle, above this it is ductile, and this transition temperature is low. But if you cool slowly after tempering, then you will find, say for such steel, if you try to find out transition temperature, say it is quite high. So, many of these steel, if they become brittle, it is quite risky. You have to handle, say suppose turbine blades etc., which are made of such material, hardened and tempered steels, and they are susceptible to such kind of temper embrittlement. Then in fact, you can you will find that service exposed materials have become brittle. So, therefore, you have to handle with care during any inspection. You should not hammer and cause crack to initiate, and that can cause a severe problem. So, you have to be careful. You must know the whether that steel is susceptible to such kind of embrittlement and take appropriate precautionary measure when you are performing such any examination of any service exposed components. A quick look at some of these application and properties. Primarily, let us look at we will take up alloy steel separately, and let us see that with plain carbon steel, this plot gives you the range of properties that you can expect if you change from nearly 0 to 1% carbon. The strength, it can increase significantly, and in fact, you will find that if you normalize, you get one kind of say let me try to find out the sheet. I mean, okay. So, all these strengths, if you say that if you quench, then with a percentage carbon, or if you have this can become very high, that tensile strength can be very high depending on the carbon content. You can have a very high tensile strength, whereas elongation, if you increase strength, this elongation will always, you will find that with carbon content elongation will go on decreasing, but strength will go on increasing. If you have but this strength will also depend on the type of heat treatment that you give. Say yield strength, if it is a normalized, this is the plot it follows. If it is a tensile strength you are measuring, this is how it will follow. But if you harden, then you can get substantially very high. And in fact, in a hardened steel you will find the difference between tensile and yield, that also goes becomes smaller, but ductility and toughness will decrease with increasing percentage carbon content. But after hardening, if you temper, you can improve ductility and toughness. To sum up, so you see some applications which are listed here: high carbon steel, particular application, cutting tools, dies, then spring, they are used in quench and tempered conditions. We have wear ropes, these are also high carbon steel, but they are given a very special heat treatment. We will learn about it little later, and here the strength can be as high as around 2000 kind of MPa, and they are used for wear ropes and load carrying, and that even bridges, etc., rope bridges are made up of these type of steel. Then medium carbon steels are used for rails, axle, shaft, gear. Then low carbon steels, bulk of the material belong to low carbon steel. They have bulk application is structure application, bridge, car, ship, and one of the important property that they must have apart from the strength and ductility, they must have good weldability. So, they should be weldable, whereas these materials they will be extremely difficult to weld. And I think here quick look as a determination of MS temperature. One way you can do, take a sample, quench it below MS, then quickly raise this temperature and then quench it, and then look at the microstructure. So, martensite which forms here get tempered over here, and this tempered martensite when you develop microstructure will appear dark. So, looking at that microstructure you will be able to find out amount of tempered martensite and fresh martensite, and if you plot percentage of tempered martensite you will find you get this type of plot. So, with this we finish this topic on that heat treatment. What we looked at, we have today we looked at hardenability, factors determining hardenability, we looked at heat transfer during quenching, looked at effect of alloy elements, we looked at alloy element effect on tempering kinetics, we talked about temper embrittlement and also determination of MS temperature. Thank you.